All right,
Yes,
I
it
think
started.
that's telling me that it started recording. So good afternoon, everyone. Thank you for joining us on a Sunday afternoon for this tutorial. It's titled Quantum Communications in Practice, which is always a bit of a challenge because most of us work in a theoretical domain. Right? But I put in enough information in this talk or this tutorial that I'm hoping it will give you the pointers that you require to build practical quantum key distribution systems. I do have the chat window open, so if you want to ask me a question during my talk, please interrupt me. I don't have any syllabus as such. A brief introduction. I come from the Center for Quantum Information, Communication and Computing. We work on quantum networks, quantum computing, and quantum information, as the title suggests. And in there, we do work on quantum keys, network secret sharing, which is some of the parts that we will cover today. What we do work with are photons, and there are two properties of photons that are of interest. One is entanglement and one is superposition. This little cartoon out here gives you the formula for the energy of a photon, is h nu. And actually, we may have the opportunity to revisit that during this talk a little bit. If you look at the motivation for quantum communications, it's basically around the idea of security, right? Now, what we say it is a motivation today is because it's always ready, right? And it keeps getting better, undoubtedly, but it's ready today. So we should really be using what is available to us today. We can use existing fiber optic or free space infrastructure. And the other parts of the talk, which I will focus on, are the quantum key distribution themselves. How does it happen? What are the modes and methods? What is the hardware? What are the challenges? I'll briefly touch about quantum networks. I know you've had a talk earlier today on quantum networks, so I won't spend too much time on it. And we'll also discuss what the national status is. Right? Okay. Just give me a, apologize for this. This is irritating me. Here we have a picture from 2021 January of the network that was set up by China between the two cities of Shanghai and Beijing. And in the middle, there are two other cities, Hefei and Jinan, right? And what this is a secure node network. So the yellow circles with black dots are secure nodes. The arrows are the four cities. And at each of those four cities, they have metro networks set up with quantum quantum communications. They've also got the satellite thing running between China and Switzerland. But the focus today for us is on building such terrestrial networks. Why is this useful for us? Well, there is this race towards quantum supremacy, and we will keep hearing about people having done better than classical computers, but they're solving very special problems. The holy grail for us is what is called public key encryption, and that is how we do all our digital transactions today, whether it is banking or whether it is filing taxes. And that encryption relies on what we call computational strength, right? We are assuming that there is no classical computer that can break it. But when there's a quantum computer, we know that it is insecure, and that becomes a problem for us. So on the x-axis, you have the number of qubits. If the number of qubits gets to about 10,000, then things start getting really scary for us. And but in another couple of years, IBM is promising that they'll get us to 1,000, right? So you can imagine that in about 5 years or maybe 7 years, people will no longer be able to rely on public key encryption. The question for people doing communications is, when do you know that your communication has become insecure? And the chances are you will not know until there is a leak that it has been done, or there is an admission that someone has cracked your passwords. I was reading the recent IEEE Spectrum about one of these encryptors, and they all have backdoors. The encryptors being used right up to the 1980s was built by, I think, an Austrian engineer or a Swiss engineer, and yeah, it was a Swiss engineer, and known backdoors were there in that, so that the Western world could eavesdrop on us, right? So there is that real danger that we will not know when our infrastructure has become insecure. What infrastructure are we talking about? Here's an example of some infrastructure. This is a national knowledge network. The blue lines are used for Railtel, the green is Postal, the yellow is BSNL, and of course there are all the private players also. This is the national knowledge network, which is what the National Informatics Center has leased out from these particular companies, right? And it connects all of us, all our higher education institutes, all our atomic and defense infrastructure, all our CSIR labs. So it's definitely something that we want to secure. Right? Now this is the backbone, and it aggregates traffic. Data rates can be as high as 100 gigabits per second. Right? I want you to remember this number, 100 gigabits per second. It's actually low because today's demonstrations are now at terabits per second and 10 terabits per second. So 100 gigabits per second is already becoming outdated, but I want you to remember this, that the data rates can be as high as 100 gigabits per second. Within each of these dots, you're actually running networks themselves, and this is what it would look like. You would have access networks where you've got businesses and LANs connected at about 2.5 gigabits per second. Then you have metro area networks that go up to 10 gigabits per second. And then you have the long haul networks that go up to 40 and now 100 and 1000 gigabits per second, right? So these networks also need to be secure. So one of the things about quantum communications is, as you learn as we go along, is that it's very hard for it to work across networks. We usually do links. We can do 2 links, 3 links. Getting it to work across networks means we have to start rethinking some of this infrastructure and the way it has been laid out. So what is practical? That was part of the title of the talk, right? The first question about practicality is who pays for it, right? And what is this it? It is your data, right? And there are 2 ways of stealing data. You can steal it while it is at rest, or you can steal it while it is in transit. So quantum communications is trying to protect data at transit. Now, if you get your password and you write it on a piece of paper and somebody steals it, that is not something that quantum communications can protect against. So what limits it is actually human fallibility. Many people write their passwords down, right? Or we reuse the same passwords, or we don't change our passwords. I know that my passwords have not been changed for much longer than I would want them to be, despite all the warnings I get, right? The technology can also be a limitation, right? There are losses, there's timing jitter, and there is speed with which it is transferred. It's actually interesting that yesterday I was doing something else and I could hear an echo of myself when I ran, when I was talking into one device and it was coming back to me on another device. There was a definite time lag. So although we think speed of light is the fastest thing there is, when we're talking of these kind of distances, the speed also becomes something of an issue. Can we rely unconditionally on quantum mechanics? We rely on our understanding of quantum optics, information theory, and coding and telecommunications. But that is a very theoretical understanding. And I always like to say this, you believe in all the physics, you believe in the information theory, but you must rely on engineering. A poorly engineered solution is not secure. The engineering is going to determine whether or not you're meeting the standards of information theoretic security that quantum communications offers. So we secure data in transit, right? And I've given you a link out here and I'll post this in the chat box. So you can actually go in and take a look at it, and you will find that it's actually a way to just, tap fiber optics. And if your data is not encrypted on that, then you will find that anybody who wants can tap into it. Right? And it's a very simple device, and we can run these demonstrations in our labs also. So we secure data in transit. But how do we secure it? There is something that called one-time pad. But the one-time pad requires that the length of the key and the length of the data be the same, or rather the key rate and the data rate have to be equal. I was reminding you to think about 100 gigabits per second. Now, our key rate is never going to be 100 gigabits per second. That is the classical data rate. Our key rates are usually going to be in megabits per second. So you already have a flaw there that we cannot prove information theoretic security unless we are only talking of a low data rate, let us say a video call, which requires a megabit per second. We could probably do that with quantum communications. But we cannot do aggregated traffic from all the metros down the backbone simply because we will not have 100 gigabits per second of key rate. So some of the questions that we ask practically are, how do we distribute the keys? How frequently can we change the keys? And how random are our keys? What are these keys that we're talking about? It's a little bit of a primer out here. We're talking about key distribution, where Alice is trying to send some information Y over to Bob, and Bob is also replying with some information. And there is a key that allows them to encrypt and decrypt on either side. And in the middle, there's an eavesdropper, Eve, who's all access to both YA and YB, and is trying to determine this key K, right? And the most common protocols are the Diffie-Hellman protocol that depends on the assumed complexity of a discrete log problem, right? And I won't go into details on that, but you can look it up. What we are trying to do instead is to understand what is this key distribution about, right? So public key cryptography has many ways of doing it. The most popular ones are in the middle out here. There is AES and there's RSA. RSA is likely to be insecure with a quantum computer. AES is quite likely to be secure with a quantum computer, right? But it means it's harder to do. But these are all quite likely and likely. It's not guaranteed. Guaranteed is only the one-time pad, right? And again, the one-time pad is limited by its key rate because the key length has got to be equal to the message length. So this is an assessment of the security that you have, right? And it will tell you that in the post-quantum security level, a lot of these keys will be broken. And in the pre-quantum and post-quantum, there is a definite difference. And of course, one can argue that you can keep making your keys longer and longer. But as an alternate, you can also do quantum key distribution. And what we are relying on out here is that we are using single photons that are being transmitted from Alice to Bob. And you're throwing away all the bits that are given to Eve. So if Alice sends 1,000 bits and only 10 bits reach Bob, even if Eve gets 990 bits, we will set up the key only with those 10 bits between Alice and Bob, right? So those 10 bits become your key. And once you have the key, what you're doing is an encryption. So you're going to do something like this, right? You're going to take this key, and in this particular cartoon, it's called a public key and the secret key. And you're going to convert Alice's plain text to a ciphertext, and then it's going to decrypt it back to a plain text. Now, the idea is to do this with single photons. And if you can do this with single photons, then you're ensuring that if there is an eavesdropper, that eavesdropper does not get any information by eavesdropping on this channel between Alice and Bob. This is just one example of quantum communications. It's the most basic example. It's not the only one. There are other ones. So this one is a more complicated one on secret sharing. It was proposed in 2015. And this is an interesting idea that if you're trying to share a secret between many parties. So here, for example, there's Bob, there's Charlie, there's David, and there's Elizabeth. Either all of them have the information or none of them have the information, right? So it's like going to a bank and saying that you need 4 keys to open the vault. Alice has the vault, and only if all 4 of these people come together can they collect the information that's inside the bank vault, right? So there are ideas out here that can extend quantum communications to beyond just key distribution. This is the first time I'm showing you an optical circuit, so I'm going to very quickly take you through what is being shown out here. You'll see out here there is a pulsed laser, there is an optical attenuator, there is what is called a circulator, there's a 50-50 coupler, there's a phase modulator, a polarization beam splitter, single mode fiber, and then more phase modulators and single mode fibers. On the receiver side is a single photon detector, right? So we will go through some of these components that are used to build the systems up and understand them. People who have done fiber optic communications are familiar with a lot of these components. When you start doing quantum communications, you use the same components, except that you're really working at the single photon level, so you need single photon detectors. This optical attenuator is attenuating the laser down to single photon levels. And that is where the quantum optics part of the setup comes in. Most of these devices will work either in classical or in quantum modes. So let me take it up one level again and say, this is what is actually going to happen. You're going to have a QKD system. You're going to have a quantum channel between Alice and Bob. This quantum channel is going to run, in this particular picture, I put it as 100 kilobits per second. Toshiba has said that they can take it up to 10 megabits per second. But the standard communication channel will be running at 100 gigabits per second. So there is always going to be a factor of 1,000 or 10,000 between these two. If you want to understand what that means, it means that you're using your same password 10,000 times, right? And that is actually insecure, right? So you have to pay attention to that if you want to build a fully secure system. Out here, there are 4 other steps. These are all classical steps. Authentication. How do I know that this is Alice and this is Bob? Key sifting. So I mentioned that we only build the key using the bits that have reached Bob. So in my example, I had said if Alice sends 1,000 and Bob receives 10, then our key length is 10. We do not worry about the remaining 990. That's not entirely true, but for now, let's say we don't worry about the remaining 990. So what the sifting is Bob telling Alice that these are the 10 that I received. He does not reveal the values. He does not say it's 10110 because that would be useless because it's going on a classical channel. What Bob is instead saying is, I received the photons in time slots 1, 23, 72, 343, and so on, right? So some random set of time slots when he receives the photon is what he's revealing. Since Alice has sent the information in that time slot, she knows what the bits were. He knows that it was a 10, 110, and so on, right? So that is the process of key sifting. Then you have error correction, because even in that communication channel, there could be errors. Alice may have sent a 1 and Bob may have received a 0. So we do error correction. And then because there is all this classical communication happening out here between Alice and Bob, there is a step of privacy amplification. So if you're a communications engineer, you would be actually doing some of this stuff classically also. We are using the same schemes to bring it down into what we call quantum communications, and saying that these schemes allow us to maintain the security of the information that is transmitted over the quantum channel. Once you have all that, you get a secret key, which then goes into an encryptor. And on the other side, there is a decryptor that will decrypt it. So you have a channel that is now secure. Okay. Let me take a brief pause out here and tell you that there's a very nice tutorial. It's from the IEEE Communication Surveys and Tutorials published in 2019. This picture is taken from that paper, and you can actually go in there and try to understand it a little better. There are many things in this picture. So we are particularly working on the things that are in this dashed red box. It's called a discrete variable, where we're talking of ones and zeros. We're looking at optical fibers, and we are using single photon detectors. We have started now working on continuous variable, free space optics, and homodyne detectors. And of course, there are people in India now working on satellite-based free space optics. What we are doing is a scheme called prepare, transmit, and measure. So you prepare a quantum state, you transmit it over a quantum channel, and then you make a measurement. Right? Putting this entire thing together, if you can put in a bunch of optical fibers, free space optics, and make them all talk to each other, then you end up with a quantum network where you have satellite-based systems talking to satellite transmitter and receivers, base stations, those being connected on terrestrial fiber optics to each other over a quantum network, right? And the protocols are all different. So the most common protocols are BB84, E91, B92, and variations of those, right? Okay. So now I'm going to, this was sort of the background, and I'm now going to take you back to the physical layer and say, okay, how do we actually do something like this? To do that, you need to understand some of the properties of light. The properties of light that we find interesting are the polarization, which is this top left diagram, where you have the electric field polarized vertically and the magnetic field polarized horizontally. And the wave is propagating along the x direction out here. The other property is dispersion. You know, in high school, many of you would have done experiments where you shine white light on a glass prism and you'll end up with the different colors of the rainbow. The rainbow itself is a good example of dispersion. But this is not only in the visible region, it's also there in the ultraviolet and infrared region. The other properties are what we call radiation pressure and phase. So particles and photon numbers create radiation pressure noise. Wave-like behavior has a phase. The phase is basically, this is a wave out here going up and down, and this is what we have drawn is a sine wave if the zero is at the center. And you'll notice that the two of them are offset. That means one of them has a different phase than the other one. In the first picture, both have the same phase, but they have different amplitudes. So these properties are actually related by an uncertainty relation, and that is what we rely on. So for example, out here, you cannot measure the phase of a single photon. So you have these kind of properties that people use. Another property that is like this is also the polarization, right? There's an uncertainty in the polarization of a single photon. Okay. What else do we know about phase? We know about phase again from high school experiments or maybe undergraduate experiments of diffraction. So this is a single slit experiment. You'll see out here that there is a peak at the center and small peak or small maxima on the two sides. And this is what happens if you have a large slit and a wave coming in. If you have a small slit and a wave coming in, then you get a more pronounced diffraction pattern, right? In 2 dimensions, you get what are called rings or Newton's rings. Now, what happens if you put 2 slits? The Young's double slit experiment was run almost 2 centuries ago, and you would see that the wave fronts, which are spherical in nature, would interfere with each other, and you'd end up with maxima and minima corresponding to where there was constructive and where there was destructive interference. And this sort of an experiment was then repeated with electrons. And when it was repeated with electrons, they found that it matched this behavior of interference with maxima and minima. Now, this is very counterintuitive, because if electrons were particles, then they would not be able to interfere with themselves. Out here, what is happening is the wave is interfering with itself. Whereas the first electron does not know that the 10th electron is going to come. So it cannot be interfering with the 10th electron. It is interfering with itself and then coming up with this kind of a maxima, minima pattern. That was the first quantization. In the second quantization, you replace the electrons with photons. And you're saying that, wait a minute, the wave that we thought of light is now actually a particle. And it will also behave like this if you use single photons. So we came up with definitions of non-classical light. right? It was a very famous experiment by Hanbury-Brown Twiss, and it won them the Nobel Prize, where they showed that you could actually observe non-classical behavior of light. This cartoon out here is very nice. It's taken from a thesis where it gives you some other properties of light. So in the first figure, there's photon bunching, where bunches of photons come together. And there is something called a coherence time. The coherence time is the time over which you have a wave-like behavior and you can measure the phase of the photon. And this is typically what laser light is. Coherent light has a random distribution. It does not have photon bunching. And then you have photon anti-bunching. So these are actually true quantum emitters where they're emitting single photons. And there are many ways of building such photon quantum emitters, right? Okay, so now...
So one small doubt.
Yeah.
This diagram from left to right, is it time or is it space?
It's time. I mean, it could be anything. It's time at this point. It's time, right? If it's
Okay.
It could also be space, but I think it's easy to understand if it's left to right is time, because especially since I've written coherence time out here. I mean, okay. So non-classical light in the Hanbury-Brown Twiss experiment was basically saying, look, let me put a source of light out here and put single photon detectors and analyze it. And there is some delay in the times between these two detectors. If that delay is 0, then I will see a statistic of G2, which is non-classical. So what that means is if there's one photon coming in, it can either go to this detector or it can go to this detector. It cannot be coincident. If there's more than one photon, then it can, one will go here and one will go here, and you'll get a high rate, right? So if there is no delay between the two, then you'll get, with a single photon source, you'll get a non-classical dip out here, right? This was the most famous experiment by Hanbury, Brown, and Twiss. And they showed that you can get what are called sub-Poissonian statistics. Sub-Poissonian statistics is where this dip is very pronounced and it goes actually less than half, or it goes less than 1. But today, in some cases, we'll say that it goes less than half. So this is one way of measuring whether the light you're using is classical or quantum. The other example is polarization qubits. And here, I've given you an example where horizontal polarization is what is called ket0 and vertical polarization is called ket1. And you can run computing like this. And this is an example of how quantum computing is done. It's using what are called half-wave plates and quarter-wave plates. But that's not really the topic of our current discussion. For us, it is just sufficient to say that there are these properties which are classical properties that we have now kind of absorbed and said we can do quantum optics and quantum communications with it. A simple example, the first and simplest example is that of a quantum random number generator, right? If I take a single photon and I hit it on a beam splitter, the Hanbury-Brown Twiss experiment would tell me that this single photon cannot hit both these detectors simultaneously. If it hits the first detector, I will call it a 0 bit. If it hits the second detector, I'll call it a 1 bit. And this gives me what is called path superposition, because this photon, before it hits a detector, is in a superposition of either the top path or the straight path. So this is reflected light and this is transmitted light. And in this superposition, as soon as it hits a detector, it collapses into a 0 state or a 1 state. The question you asked about spatial, whether that stream was spatial or temporal, in this example, it's actually spatial. So if you let that photon go out through a slit, it will spread out over this diffraction mask, right? And depending on where it hits it, you can come up with a 1 and 0. You can say alternate pixels are zeros and alternate pixels are ones. And depending on where this photon hits this screen, you can decide that you've got a random number generator, right? And it's a very easy way of building a random number generator. The time of arrival is another thing, right? Since those photons are anti-bunched, you do not really know when they are going to arrive. They're not it's not, you cannot predict when they'll arrive. And so you can just do a very simple modulo 2 on the time and you'll get a quantum random number generator. Shouldn't both detectors be equally spaced from the beam? Yes. So if they're not equally spaced, there'll be some delay and you account for that delay, right? So the diagram is not perfectly accurate. You would want it to be equally spaced, but it's not possible to always make it equally spaced. Remember, it's important to ask this question: what is the size of a photon, right? And it's very hard to answer that. The size of a photon depends on the experiment you're doing. If you think of a laser being focused to cut metal, then the size of the photon out there is the diffraction limit. It's lambda by 2. Okay, so if it's 1 micron, then it's 500 nanometers spatial extent. However, if you think of the speed of light and you say I'm sending a pulse of light which is 1 nanosecond, then that will occupy few 10 centimeters. So that's clearly not 500 nanometers. So the size of a photon is not very clear. It depends on the experiment. So the arrival time of a photon is also like that. It depends on the experiment and it's not critical because we can always compensate for the delay by adjusting our clocks. Okay. So this set of experiment we combined this along with time of arrival and we ran an experiment, and it's a very simple experiment. You take a laser source, you attenuate it, you send it through a coupler, attenuate it again, and all this attenuation is required because the coherent source or the laser that you're using is actually 1 million photons, 100 million photons. So what these attenuators are doing is you're bringing it down to a single photon level. And once you bring it down to the single photon level, then you can run an experiment like this, which basically says take these single photons and then they send it through either path A or path B. And because there's a delay, this photon will come at a different time instant than the ones that come at path A. And by looking at the clock, I can decide whether it is coming through path A or coming through path B. And that tells me whether it is a 0 or a 1, right? And this was actually work that we had presented about 3 years ago at NCC, right? And it passes all the tests. So here's a very important challenge, right? This is is this truly a quantum random number generator is the question. All the tests that we have are actually classical tests. ENT, NIST, and dieharder are classical tests. So I could take any classical test that passes everything very well and make a claim that it is quantum. True quantum random number generators must pass quantum tests. And there are a few of those that are being postulated by a faculty in Berkeley, Vazirani. And you have to run those kind of tests to say that it is actually a quantum random number generator. Right? I'll give you another example of how we use the properties of light to do quantum optics. Right? Here is what is called an optical fiber, and most people use single mode fibers. Becoming popular are something called few mode fibers. In a few mode fiber, in this particular example, there are 3 modes. And well, actually there are M modes, but the arrows are showing mode 1, mode 2, mode 3. Out here, what is important is this transmitted 1 and transmitted 2 and received 1 and received 2. We'll ignore the, received M and received 2. We'll ignore the more complicated ones because we are going to look at only these 3 modes. Now, a mode of a fiber, the lowest order mode of a fiber is like this. It's spherical, circularly, cylindrically symmetric. The modes of the higher order modes are degenerate. They have 2 lobes. And the 2 lobes could be horizontal or vertical. Now, my definition of horizontal and vertical is also arbitrary. They could have been at an angle, and this would have been the case of one of these, and the perpendicular one would have been the other degenerate mode. So it's possible to launch light into a fiber, a few mode fiber. Let us say I launch LP01, and then I bend the fiber a little bit. When I bend the fiber, because of the change in the stress, the fiber is no longer a cylinder. It is squeezed on one side, and so power will couple from the LP01 to the higher order modes. But which one does it couple to, we do not know, right? And so if you send a single photon in a single mode fiber and then couple it into the higher order modes, it will couple into either the first one or the second one. Both are degenerate. There's no preference. So you'll get 50% of the time you'll get a 0 and the 50% of the time you'll get a 1. So this was also an experiment that we did. It was, I think, sometime in 2020. And you start with a laser and then you run it through what is known as a non-mode selective photonic lantern with a 2 meters of few mode fibers. And again, you send it out through a mode selective photonic lantern. So in the non-mode selective photonic lantern, what you're doing is you're coupling light at the lowest order mode. And then in the 2 meter few mode fiber, the light, the photon moves into one of the other modes. And then I can pick it out depending on which mode it comes out here. I can decide it's a 0 or a 1. Now, interestingly enough, in all my experiments, I always use a single photon detector, but I use only one of them. I don't use two of them. I put a 7 nanosecond delay and I say I'm going to use one of them. The reason to keep doing that is because these are not ideal detectors. They also have their own, idiosyncrasies. So you don't want one of them to be running at 10% efficiency, one of them to be running at 11% efficiency, because if you do that, you'll get more of the second kind than of the first kind, right? So by just adding a delay line and keeping track of the time, we are able to say whether it is a 0 or a 1 on using just one detector. It also helps that each detector today costs either 20 lakhs or 1.2 crores. So, you really don't want to spend too much money building a random number generator. So that's why having just one detector is useful, right? So this also was a very good experiment for us and it worked quite well. Right? So what are these detectors made of? And I'm going to now take you back a little bit to classical optics for you to understand what our limitations on technology are. See, on the top out here is a graph, and we'll talk a little more about this graph, but this is a graph of the attenuation of light in silica fiber at different wavelengths. And this graph actually goes down till about 1600 nanometers and then starts going up again, right? This reason it goes down is because there's Rayleigh scatter, which is inversely proportional to the 4th power of the wavelength. And that's what this curve is. In the middle out here around 1400, there is an OH peak or a water peak. So there is some residual water molecules in the fiber and they absorb light. So traditionally, when fiber optics first started, people used 850 nanometers because they had optical sources made of gallium aluminum arsenide. But the loss was very high. And when we say it is very high, we say that this is about, let us say, 7 decibels per kilometer. 7 decibels per kilometer seems like an arbitrary number, and I'll talk to you a little bit about those arbitrary numbers in a bit. The second telecom revolution was at 1310 nanometers, and that was before the OH peak. And that is where we had other optical sources. And finally, the third telecom revolution was at 1550 nanometers, where this dip is out here, and you have the lowest loss. At this dip, you have 0.2 decibels per kilometer at 1550 nanometers. What does a number mean for us? It means that at 100 kilometers, I will have 20 decibels of loss. Now, this is a log scale. 20 decibels means if I send 100 photons, only one photon will reach after 100 kilometers. So just think about this. Only one out of 100 photons reach. Alice sends 100 photons, Bob receives 1 photon. Alice sends 1,000 photons, Bob receives 10 photons. That is why I was using that example earlier. 1,000 to 10, right? The rest of the photons are going to get lost in the fiber. Okay. We have to understand that a little bit, but you'll understand this here, that the amplifiers are also made in these particular regions. So there is an erbium doped fiber amplifier for classical communications that works at 1550. And this is the reason why all our telecommunications is working here. But that puts a limitation on us because we have to work with either Indian gallium arsenide or germanium detectors if we are going to work in this band of 1550. If you're going to work at 850 nanometers, then you can work with silicon photodetectors. So we cannot mix and match technologies very easily. This wavelength depends. If you're in free space, you can use 850 nanometers. If you're in fiber, you can long distance fiber, you can use 1550. If your distances are not very long, you can use 1310. So your metro area networks, fiber to the home that you're getting today is actually using 1310 nanometers, right? It's a little cheaper and you don't need to have any amplifiers and you don't really worry too much about the loss. But if you're talking of between cities, then you are definitely doing 1550 nanometers. So what do you do once you have these detectors? Okay, so this is how you build a single photon detector. This was done by a student of mine almost 12 years ago, 13 years ago, from 2008. And it's a very simple construct. You take a detector, you reverse bias it, and then when there is a photon, you also apply a trigger pulse or a gate pulse, and then you'll get an output. If there is no photon, you get this blue curve. If there is a photon, you will get this green curve. If there are more than one photons, then you will get this red curve. So as you start increasing the power, so 65 and 68 dBm, these would correspond to 2 and 1 photon on an average. And so the single photon would give you this green curve, and the multiple photons would give you this red curve. The important thing is this bias is basically showing you the difference between what happens when there is a photon and when there is no photon. So the blue is when there is no photon. So if you can actually apply a gate pulse that will take you up here, and then the photon arrives at the same time, then you shoot up out there, and then you come down and sit back here. So applying a 3 volts bias would mean you're going from 65 to 68. So you're applying it out here, and if there is no photon, you come back to 65. If there is a photon, instead of coming up here, you suddenly go up there, right? So this becomes the signal to noise ratio that you have, and by measuring the voltage across this resistor, you just get sort of the output or a click. So you put it to a comparator and you get a click that's coming out. So it's not very difficult to build, except that it needs to be cooled. So when we built it the first time, we had 2 stages of a Peltier cooler. It would take us down from room temperature down to minus 40 degrees below room temperature. Now, room temperature is different. In Bangalore, it's cooler. In Madras, it's 40 degrees. So 2 stages of Peltier cooler were not working for us. So my student would wear a jacket and turn the air conditioner down to 20 degrees so that he would operate at minus 20 degrees inside the detector. Right? Today, there are more advanced. You can get 3-stage detectors, 4-stage detectors, and they take it down to about minus 60 degrees Celsius. Why do you need to take it down to a colder temperature? Because there is noise at higher temperatures. Temperature is a measure of the entropy, and so at a higher temperature, you actually have more noise. By cooling it down, we are reducing the noise, and we are able to detect and measure this kind of behavior. Right? Now, how reliable is this behavior? Well, it's fairly reliable, except that once it comes onto this green curve, it does not come down instantly to the blue curve. It takes time. And that time, if you look out here and notice the bias out here again, I'm applying a 67 volt bias and a 67.5 volt bias. At 67 volt bias, we have the recovery time of the order of 1 microsecond, but 67.5 volts, the recovery time has gone to the order of 3 microseconds. So it's called the hold off time. Now, if I have a 5 microsecond hold off time, that means my raw key rate can only be 200 kilobits per second. If I have a hold off time of 1 microsecond, then my raw key rate can be 1 megabits per second. And now you should understand, you should be able to tie this together and say, wait a minute, my classical communication was running at 100 gigabits per second. My keys are going to run at, if I'm lucky, 1 megabit per second. But if I'm not lucky, maybe 100 kilobits per second. 100 kilobits per second to 100 gigabits per second is a factor of 1 million. So I'm using my password 1 million times. All right. So that is something that one has to be aware of, that quantum communications, at least quantum key distribution, the way it is practically implemented, is not unconditionally secure. It is secure to the extent that our key rates are about 1 megabit per second. This is just a very quick caricature to show the other property, polarization. You may have already seen this yesterday. You can do coding using polarization of light. You can do either the vertical and horizontal basis or the rectilinear basis and the diagonal basis. And again, what is happening out here is a very simple idea that a photon has information both in its polarization and in its timing. And what we are doing is we are splitting that information. We are splitting it and saying that we'll either send it in one of these basis sets, or we will not reveal the timing at the same time. So because that information is split, there is an additional security that you achieve by doing that. You could see from my earlier slides that there is a commonality. You remember those pictures that I showed you of the few mode fibers which were degenerate. So because those few mode fibers were degenerate, and I think it's this picture, you can see that instead of using polarization, I could also use these as zeros and ones. If I am only propagating this, I could send light at some diagonal, and it will be in some superposition of these two states, right? So there is this commonality that you have once you understand the optics, that you can do different types of things. What we're talking about out here was the BB84 protocol, which was actually announced in Bangalore at a conference by Bennett and Prasad in 1984. Right? And this is a very common picture that is taken from the website of, I think, ID Quantique, where they show how this polarization-based quantum key distribution is implemented. Okay. Let me not spend too much time on this. I'm assuming someone has explained BB84 to you yesterday. Is that right?
Yes, sir. It was covered yesterday and today.
Yes. So I will not spend more time on that. Right. Practically, I think more easier to implement is what is called plug and play QKD. Right. But before I do that, I should ask a question. Right. Why is BB84 with polarization hard to implement on optical fibers? Does anyone know the answer to that? Was that discussed?
It wasn't discussed, but maybe I'm guessing the polarization information is lost, the phase.
Yeah, so polarization is not maintained very well in optical fibers over long distances. So because of that, people came up with other schemes where they use the phase of the light, and plug and play QKD is one such example where they use phase of light, and that uses something called a B92 protocol. And okay, let me explain to you why plug and play is nice. Plug and play is nice because the lasers on one side and there's a Faraday mirror. What a Faraday mirror does is it rotates the polarization. So when it goes forward, if there are some changes in polarization, then on the way back, it gets countered on the way back. So it gets reversed on the way back. And so when the measurements are made out here on these detectors, you will find that you no longer need to worry about any polarization fluctuations in the quantum channel. So that's what made plug and play QKD attractive, and it was demonstrated under Lake Geneva in 2002, right? But this is my little smiley that says nothing is ever plug and play. If you try building it, you will find you can't really do it, right? It's not as simple as it looks out here. And that's because there's a lot of engineering that goes into doing something like this, right? But it's on the face of it, it's a very neat little idea of using a Faraday mirror. Right? The information is again sitting on this phase phi A and phi B. When phi A and phi B are equal, then you get detection coming down on port 1, and when they are unequal, you will get detection coming down on port 2. How do you make sure it comes on port 2 is another component out here called a circulator, which basically the laser that comes in circulates and goes down there, comes back, and then it interferes out here. So this is what is called a delay line interferometer, and this interference will then cause it to come either detector 1 or detector 0. Now, what is interesting is this, right? This delay line construct means that you have to understand phase of the light. That coherence time that I had described earlier means that the delay line construct has to be smaller than the coherence time. If it is not smaller than the coherence time, then interference does not work, right? So a lot of these challenges about interference come back to some of the raw properties of the photons that we are measuring. This was an example of us doing what is called the B92 protocol using phase to carry information. Two phase modulators with a spool of fiber in the middle. And when the phase modulators have the same phase, then you will get constructive interference. When they have different phase, you'll get destructive interference. And there is a formula for the visibility, and we got about 0.96, which we thought was quite good. Right? A lot of these are statistics because these are single photons. You cannot, so this gated avalanche photodetector is making counts. So these are statistics, and you'll get error bars on all your measurements. Right? There is another version called differential phase, which is better. So in this particular example, you have to have spools of fiber between the two phase modulators. And this is, again, harder to do because that means you've got a single reference. And that means that reference has to keep going between Alice and Bob across 100 kilometers. In the differential phase, which was proposed in 2002, they basically put the information between two pulses of light, between D and D, between C and D, between A and B. And then they ran it through this delay line interferometer. And if the difference between A and B was equal to the difference between D and C, then they would get constructive interference. Otherwise, they would get destructive interference. And that sort of told you again whether it was 0 or a 1, right? So this differential phase actually is again a very common communications technique. Differential phase, quadrature phase, these are all ideas in wireless that are continuously used. They're also used in optical communications these days, right? The DPS QKD ensured that you're not really worried about fluctuations in the fiber channel because the difference between these two pulses is of the order of a nanosecond, and the fiber channel does not vary in phase over a nanosecond, right? So the time constants become important. What is the time constant over which polarization will fluctuate? What is the time constant over which phase will fluctuate? These kind of time constants become important. We extended that to do what is called three-state DPS QKD. And you can see out here that we have allowed the photon to go into a superposition of 3 states. And then we apply a phase between 1 and 2 and 2 and 3. Now, what is the primary difference between this experiment and the previous experiment? In the previous experiment, they have different pulses of light. So each of these has its own state. As long as a laser coherence time is long enough, then these could be construed as a photon being in a single superposition state. But that's a very, very strange construction. This, on the other hand, is a more understandable construction where if you have a single photon, because of these delays, it comes out as a superposition of these 3 time bins. And then you can use your quantum random number generator on a phase modulator and apply a phase between the first and the second and the second and the third. And that's sort of shown by this color coding out here between red and blue, right? So your superposition state is now in time. You have time instant A, time instant B, and time instant C. And then you have a probability of detection. The detector, again, is going to be a delay line interferometer where you're interfering, looking at the difference between these two and the difference between these two. And depending on whether they're equal or unequal, you will get constructive or destructive interference. And the different paths that are possible, there are 3 out here and there are 2 out here. So you have 6 different paths possible. You can count the probabilities of detection. And you will find that if they take the longer path and the shorter path out here, you will get 1/3, or you take the shorter and the longer on this side, you'll get 1/3. But if you take the shorter out here and the shorter out here, you'll get 1/6. And you take the longest out here and the long out here, you'll get 1/6. So again, we have made it hard for an eavesdropper because we have used time bin superposition. Okay. It's a very interesting construct because we've shown that actually time bin superposition is the same as spatial superposition. And that was another piece of work altogether. But again, talking about practicalities, it's not easy to set up because you actually have to get in a classical experiment, you have to get B and C equal in amplitude and A and C prime equal in amplitude. And only then this experiment will yield these kind of probabilities of detection, right? So you run classical experiments, you try to balance them all out because there are losses along all these things. That this is twice the length of fiber. It may not have, it won't have the same loss as a single length of fiber. So one has to balance these things out and then try to achieve what we call theoretic. Now you'll notice out here, the pulse train DPS was dying at about 100 kilometers, whereas the four-state DPS can go up to 120 kilometers, right? So it's a little better than doing just the regular pulse train DPS. This was our demonstration where we got it to go to about 110 kilometers, right? So 120 was the theoretical limit. We got to go to about 110. We did it with a quantum bit error rate of less than 20%. The quantum bit error rate is actually something that we need to worry about. My examples are actually not quite correct. If Alice sends 10 photons and Bob, Alice sends 1,000 photons and Bob receives 10 photons and Eve receives 990 photons, then that is not a secure channel. Normally, rule of thumb, your quantum bit error rate should be less than 20%, right? Only then you can prove security on your quantum channels. If your quantum bit error rate is, I don't know, 990 out of 1,000, that is 99%, then that channel is actually insecure, right? And sometimes people ask me, what do you do out there? I say, well, you just forget about it. If there is that kind of losses, then you just forget about it. It's like somebody's gone in and cut your fiber. You cannot do anything about that. The other way to do it is time multiplexed detection. And this is what I tell you is that we always wanted to use a single photo detector. So we put an extra delay line out here. And then we time multiplex the two together so that we have one detector with the same characteristics and we don't have any bias, right? I won't spend too much time on this data. But again, out here, we got 20% bit error rate. What is in red is actually the optical channel, and what is in green is the electronics. And that is where the practicalities come in. So you'll notice you have bias controllers, you have FPGA boards, you have PCs. PCs are connected on the internet. You have timing synchronization happening between the PCs and the FPGA boards. And then the FPGA boards are again controlling all the different signals that are going to the different electronic components. The TDC 7200 is actually a time to digital converter. And that timestamp that it yields tells you whether it came through the straight path or it came through the delayed path. And this delayed path is because of the destructive interference, and the straight path is through the constructive interference. So these are all kinds of tricks that we have developed over the years to make practical systems, right? So this was the other example where we are saying that it is interesting to say that temporal self-interference of a photon can be achieved. So when we run something like this, what we are saying is that the leading edge of a photon is interfering with its trailing edge. So if you look carefully out here, you have the blue line, which is the RF pulse that is applied to the phase modulator, and the red is the photon pulse, right? The optical pulse. So every time the RF pulse cuts the optical pulse, you will get a peak. It could cut it either at the leading edge or at the trailing edge. And we got two peaks out there. And what this means is that we are interfering the front of the photon with the back half of the photon. Now that is again something, it's not non-intuitive. In the original proposal, there were different pulses. And we said, hey, wait a minute, we don't even need different pulses. We can take one pulse and attenuate it down to a single photon, and then say the front half of the photon is going to interfere with the back half of the photon. And that's actually very neat, right? Because that means that I no longer have to worry about setting up experiments like this. I just have to keep RF pulses that are shorter than optical pulses, and that is possible to do today. In other developments, we have also looked at what are called measurement device independence, right? Measurement device independent means that instead of stopping at 100 kilometers, I can take my channels up to 200 kilometers because in the middle, there is charge. With every such thing, there's a complication. Nothing is easy. Nothing is plug and play. I think if there's anything that you want to remember from this tutorial, there are two things you want to remember. One is you believe in physics, but rely on precision engineering. The second one is nothing is plug and play. right? So you can propose something like this, you can publish it, but if you want to implement it, you have to again go back to doing some serious engineering. The serious engineering out here is that you have two sources, Alice and Bob, which are now 200 kilometers away, and their lasers have to be locked because they're going to interfere together on this beam splitter in the manner in which we had talked about the Hanbury-Brown twist. If there is one photon, then it can go in onto either detector. If there are two photons coming, then it will split one here and one here, or we get two here and two here. Now, depending on the interference, so if Alice and Bob have the same phase, then they will go to, they will split. If they have different phases, then they will go to either this detector or this detector. Now, that means I have two problems. I have to lock these two laser sources that are 200 kilometers apart, and I have to be able to tell with sub-nanosecond precision which of these detectors clicked, right? So building out systems like this is much harder than actually just proposing it. I think I've got time to talk about the coherent one-way protocol, right? The coherent one-way protocol is actually one of the simpler protocols to implement. All it does is it uses time. It says that the photon is going to be in a superposition of a vacuum state and a photon state. So it's either a vacuum state and the photon, or a photon and a vacuum state, and that is bit 0 or bit 1. And then the addition of a decoy state. The addition of a decoy state allows you to determine whether there's an eavesdropper or not. And again, you'll notice that the decoy state and the monitoring line at the bottom out here is using what is called a delay line interferometer. So mostly the use of a delay line interferometer allows us to work with fibers, allows us to work over longer distances, and we do not really use polarization when we are doing most of our experiments, right? You can do polarization maintaining experiments, but polarization maintaining fiber is not common, and if you're trying to take it into field trials, then it's very hard to do. This is our results of our coherent one-way quantum key distribution. We went up to about 155 kilometers before the losses became too large. And here you will see that you have a photon counts coming in the first half, followed by a vacuum, and this is a logic 0, or you have vacuum and then photons coming in the second half, and this is logic 1. And this timestamp module is in picoseconds. It's 100 picosecond. Actually, it's got 55 picosecond resolution. The jitter is what kills us, because the timing jitter between the time to digital converter and the FPGAs is also of the order of tens of picoseconds. So being able to do high precision electronics is the challenge for most of our quantum communications. Okay, I'm going to switch tracks a little bit and talk to you about the networks, just so I can show you a few things that are happening. The networks, the way we build networks is using what is called wavelength division multiplexing. We send different wavelengths of light. So right at the beginning, I showed you the glass prism, and I said, remember your dispersion. The different colors of light actually don't talk to each other. So you can set up different wavelengths to co-propagate down a 100-kilometer fiber. Then you have an erbium-doped fiber amplifier, which will amplify it and send it down for another 100 kilometers. And then you do a demux and take it out on 4 different channels. This is what a classical long-distance communication link would look like. Now, if you want to do quantum communications on this link, you can do it by sacrificing some of these channels. So these channels are on what is called an ITO grid, and there are about 40 of them around 1550. So what we are going to do is we are going to carve out a set of channels out here, let us say about 4 channels, and use one of them for doing quantum communications. However, this erbium-doped fiber amplifier is going to be a problem, so you have to bypass that using what is known as a drop and then an add. So you bypass the erbium-doped fiber amplifier and then go to longer distances, right? So that is the plan for us to build networks. This is an example of a network that is actually running in Cambridge, where they have used these different channels, 36, 37, 38, 39, 40, 41. And they've used the fact that they can generate photons. And this is a construct, again, it's called a Sagnac interferometer. And it generates photons at particular channels in the telecom grid. And they can use the timing between these channels to set up the keys between 4 parties, Alice, Bob, Chloe, and Dave, right? So this is how wavelength division multiplexing starts helping us. Now, there is a small problem with this when you go to longer distances. When they set it up in Cambridge, it's not a big problem because the distances are short. But if you go to longer distances, there's a problem. And what is that problem? The problem is, again, that the clocks will get delayed because the different wavelengths travel at different speeds. So if you go back to this picture and ask, why is it that violet is bending more than red? It's because the refractive index of violet is more than the refractive index of red, which means shorter wavelengths have a higher refractive index. The velocity of light is 3 into 10 to the power 8 meters per second divided by the refractive index. So that means shorter wavelengths with a higher refractive index will travel faster than longer wavelengths with a lower. Did I say that right? No, I think I got that. Shorter wavelengths travel slower, I think. C by n. So n is larger. If n is larger, then the speed is slower. Yeah. So shorter wavelengths travel slower than longer wavelengths. So now that you know this, you can imagine what happens when you go back to your ITU grid. You go back to your ITU grid and you'll find that they have different wavelengths, which means that some of them are traveling fast and some of them are traveling slow. And that affects your timing. So we have to understand how critical timing is for a lot of the things we do. Right? Okay, let me not spend too much more time on the timing, but I will take you through another nice experiment, which is this one, which is to say that we can generate using nonlinear crystals both wavelengths, 810 nanometers and 1550 nanometers. So in this experiment, we pumped it with 1 micron light through what is known as a second harmonic generation, which is a 532 nanometer, and then to a some frequency generation crystal, which gives me 810 nanometers and 1550 nanometers. Why is this useful? Because 810 nanometers works in free space and 1550 nanometers works in fiber. So I could technically set up a hybrid experiment where I'm looking at how photons behave at 2 different wavelengths. You can also do something like this in fiber, but instead of using these sort of crystals, you use what is known as highly nonlinear fiber and 4-wave mixing experiment. And I'll just show you the results of that. What you'll see out here is all the wavelengths are actually sitting between 1547 and 1567. And there are 2 pumps. One pump is out here around 1551, and the other pump is actually a comb line, a series of combs. And when they talk to each other, they generate photons also on a comb. This comb is useful because each of these wavelengths is now actually on the ITU grid. So if it's on the ITU grid, then you can set up those experiments like Cambridge did, which is to say, okay, you can set it up and send different photons to different people and build networks. If on the other hand, you did this kind of an experiment where you got 810 and 1550 nanometers, then you set up an experiment that looks like this, which is to say, I'll send 810 nanometers in free space, I'll send 1550 nanometers on fiber, right? So there are different opportunities for what we do in all our experiments. This is an example of our free space experiment that we're trying to, we've got 2 mirrors set up in our labs. The mirrors are actually 10 meters apart, but every round trip is 20 meters. And you can see closely, you've got 5 reflections. The receiver is sitting up here in this little, on top of this shelf. The transmitter is down here. Actually, you can see the transmitter. And because of these back and forth, you're getting about 100 meters between transmitter and receiver. Right? So we are calibrating this experiment to see if we can actually do quantum communications using this. Why is all this useful? Well, this is the reason it is useful. So we are setting up this metro area quantum access networks. The metro area, or it's a nice acronym, it's called MACAN. So the way MACAN works is we have nodes at different locations. We have IIT-Madras, we have IIT-Madras Research Park, we have the Society for Electronic Transaction Security, and you have NIC. And we are going to use all the knowledge that we have learned over the last 10 years and say, okay, you know, can we actually set up networks like this to compete with what is being done elsewhere, right? So this test bed then becomes available to us to also do a whole host of other things. There are different implementations. There are different attacks. I've not had time to talk to you about attacks. There are different attacks that are possible on each implementation. So the idea is to be able to do all of these, compare them, and say, okay, you know, which ones work better under which conditions. They will all have some pros and all have some cons. We have not actually had a chance to talk about continuous variable at all, but I think that's okay. I think I've thrown enough at you today. I should not throw more. However, I'm going to throw two last things on you, right? This one. When you're looking at quantum communications, and this again goes back to that paper from Cambridge, right, 2019. When you're looking at quantum communications and you start seeing all these things in the literature, you have to start asking yourselves, how do I compare them? And you'll notice out here different comparisons. There's Tokyo, Geneva, Haifei, Zhongsheng, and then there's a laboratory stuff, and there's Cambridge, right? And you'll notice that people are doing different things. Some of them are using installed fiber, some are using laboratory fiber, some have more nodes, less nodes. The key rates are different. So the focus is not on distance. The focus could be on other things. In all these cases, the links are less than 100 kilometers. There's 85 kilometers out here, which is probably the longest. And you'll notice the key rate drops as you go to higher and higher distances. So when people publish papers that say 500 kilometers, you should immediately be asking you, what is your key rate at 500 kilometers? Because nobody can beat the 0.2 decibels per kilometer on regular commercial single mode fiber. If they've done 500 kilometers at a higher key rate, that's because they're using specialty fiber. They've bought and installed specialty fiber. So these kind of fine prints are important for us to understand. The other one is this operation period. Somebody runs it for 1 day, somebody runs it for 600 days, 580 days. I think it's important because these systems, although they're engineered with precision, have to also be stabilized. They have to be stabilized against environmental fluctuations. I remember the engineers in QNu Labs would tell me that every time the Bangalore metro went down Mount Road, they would see higher bit error rates, right? I mean, these are the sort of things that you don't expect. Sitting in your laboratory, you don't expect to worry about whether the metro is going to increase your bit error rate. But when you're in the field, it definitely matters. So in our link, we are going to go actually using what is known as an air wave. So we are going to throw fiber over the trees. And you can imagine what is going to happen when it rains and when there's wind. But that's the reality of our networks, right? So we are going to have to deal with that when we are actually launching some of our networks. So it's not only about building Makan. Makan is one of the things that we want to do. If you have seen, if you're going to see this soon enough, it's going to go from Chennai to Delhi. We are going to say we are going to do this. We are going to take quantum key distribution from Chennai to Delhi, and we're going to hit all the metros along the way. We're going to hit Hyderabad, we're going to hit Bangalore, we're going to hit Bhopal, and then go to Delhi, right? So these are opportunities for us, right? How do we take the laboratory knowledge that we have? How do we translate that into something very practical? And it's all engineering, right? The physics has been done in the labs, and now it's all comes to the engineers to say, can we take our understanding of fiber optic communications? Can we take our understanding of information theory and put it all together and build national quantum secure networks, right? That's the goal for us. And we are hoping that we'll be able to do this. This will become something very similar to what China demonstrated between Beijing and Shanghai. And if we are successful on it, I think we would have established quantum communication as a backbone. All right. Let me stop my talk here by thanking the Q team. These are all my collaborators from different departments. There's physics, there's computer science, there's electrical engineering, there are students, there are funding agencies that support a lot of this work. So it's my thanks to all of them, without which it would not have been possible. So thank you for your attention. I'm happy to take questions.
Thank you very much for this wonderful talk. Now we take any questions which the audience might have.
Yeah, go ahead,
yes.
Yeah, hello, Professor. Thank you for this talk. So it was very interesting. Yeah, so basically, I want to know that this continuous variable QKD. So in terms of data rate and the distance, is it can it be better than this discrete variable which you have
No,
discussed?
a continuous variable is good for metro areas. I think I sort of removed my slides on CWQKD from this. It it is good for metro areas. It worked to about 40 kilometers. It's not really been done over longer distances. There may be other protocols that are possible, floodlight QKD or something like that. One has to look at it and see. But CWQKD, so far, we have not really thought of it as suitable for long distance. See, it's a very simple concept. CWQKD, the way it works is it is relying on your ability to estimate the noise of the channel. Now, the noise of the channel, you can estimate it, and it's not the zeroth level approximation of the noise of the channel, 0.2 dB per kilometer or nothing. You have to estimate Brillouin scattering, Rayleigh scattering, all of that. That's very hard to do over very long distances on fiber. So CVQKD is actually very good in free space. It may work to about 40 kilometers on fiber, but not beyond.
Okay. Yeah, so a follow-up question I want to ask is that can this CVQKD be used for like our indoor QKD between our mobile phones and maybe using this Li-Fi technology, is it possible to have short distance QKD?
Yes, so that is one very good application of CVQKD is Li-Fi QKD, right? So one could, if you can get single photon detectors with silicon uh, cheap enough to fit into your mobile phone, then that would work. I think that is a bit of a challenge. You don't need actually single photon detectors, but you need very low noise, so that may be possible.
Okay, so in CVQKD, do we still need single photon detector like for homodyne
No, you need
detection?
homodyne detectors. You need homodyne detectors, but you need them at very low noise levels. Again, right? The security is in having very good detectors at very low noise levels.
Okay, so the current limit is in terms of hardware. What is the available hardware?
Yeah, yeah, yeah.
Yeah, okay. Thank you.
There was a question in the chat box. So what
Is
to
it worth?
justify all these practical difficulties to overcome return on just national security communication military purpose? Well, it's not only military purposes. One could also look at financial purposes and say that there are many people who do not want their information that is going between banks to be lost. I think last year sometime there was a leak of information that allowed someone to walk away with lots of money because communication between RBI and some of the banks was not secured. Some such thing. I don't recall exactly what it was. But financial transactions is also something that you want to worry about. Now, things like what you and I do on a normal basis, we probably won't have return on investment. But I think business to business is definitely valuable. We have had industry. So, for example, industry very often have their plant equipment sitting at location A and their control room in location B, and they don't want anyone spying on the communication between their equipment and the control room, because spying on that means that they lose their IP. So we have had people asking us whether QKD would solve that problem. So there are potentially applications that we have not thought of yet. Is there any university certification course in India for quantum computing? Yes. I'm not sure what you mean by university certification. I know MTechs, there's an MTech program at IISc. There's also an
Yes,
MTech
it's
program at
been introduced this time.
IIT-Madras. Yeah. So MTech programs are there on quantum computing. We call them different things. We don't do it only in quantum computing. We call them quantum science and technology, because computing is just one application. You could have communication, you could have information, you could have sensing. So there are other things also. Yeah, the NPTEL
Additionally,
course has actually just started. It started last week, I think. Any other questions?
Yeah, I have a question. First of all, thank you for this great lecture today. I wanted to know We are working on a project on MDI, free space optics satellite QKD. I wanted to know your view that is it achievable in the near future with the available technology?
So the challenge in satellite QKD is orientation and tracking, which is
Yes,
actually a classical problem. It has nothing to do with quantum mechanics and
yes.
quantum optics.
Acquisition, pointing, and tracking.
Yes, if you can do that properly, then
Okay.
everything else will follow.
Okay.
So we need to get, that is what China actually did. They managed to
Yes.
get very good acquisition, pointing, and tracking, right? Now, MDI requires a receiver on the satellite and two transmitters on Earth,
Yes.
right? Now, this becomes a hard problem because now you're going to have to actually send photons to the satellite. It's not that you're going to just beam photons out there and whatever reaches the detector, you set up your key. Now you're going to have to send it to the satellite and coincident it at that time. So the satellite has got to be equidistant from the two transmitters. I haven't thought enough about it, but I can tell you, if you ask me if it's achievable in near term, I don't know how many hours of a day do you have and what is your definition of near term, right? It might be possible to do it through a balloon. Google is trying various things on its balloons.
Okay.
Something like that might be possible. Drone might be possible, but satellite, again, might be a little harder.
Okay. Thank you.
All right. Any other questions? I hope the talk was not at too high a level. Sometimes I just don't know at what level to pitch it. So I was oscillating between quantum mechanics and just simple classical optics, and I hope that was okay.
It was a good talk, sir. It was a good conclusion to the series and gives a good perspective. I enjoyed it.
Me also.
And I hope it wasn't too repetitive of what people have already talked about in your earlier lectures. Since I did not attend those, I wasn't sure.
Okay. So if there's no other questions, I'd like to conclude this talk. I'd like to take this opportunity to thank Professor Anil Prabhakar for this wonderful talk and all the attendees for attending this lecture. So thank you again, Professor Anil Prabhakar.
Thank you very much.
Yeah. So you may leave for the talk. Workshop attendees, I have few announcements before we disperse now. So the public talk is scheduled at 4 p.m. and they will try to join 5 minutes earlier, so we have no issues. Some things to note. So the recordings right now are available on the Google Drive. I will be removing the Google Drive link after Friday, and they will be later made available on YouTube. So till Friday, they'll be available on the Google Drive, and then you can make use of our YouTube channel. The problem set solutions will be given by tonight or tomorrow morning, and I'll make sure you all get it. Then for the project, please do, if you're interested, please do post in the Slack channel and maybe form teams or do separately. If you have any questions, you can always reach out to me or any other mentors. If you need anything else, you can always reach out to us. Certificates will be sent within a week. So I'll try to send it by next Sunday. All participants of the workshop will receive a certificate, irrespective of whether you submit a project or not. So I thank you all for being wonderful audience for all the lectures, and it's been a great experience for me hosting this workshop. So I'll see you in the public talk. So for the public talk, we'll be using the other link and not this. So please use the other Google Meet link. So thanks a lot, and see you.
Yeah, also I wanted to know the India Q community. Like, how do I connect with the India Q community?
So for the IndiQ community, they have a Discord server for them. So I can I'll ask them to share the details in the Slack channel. So let them introduce themselves, and they also have a website where you can contact them and all that.
Yeah.
So I'll do that.
Yeah. That would be helpful. Thank you.
Okay. Okay. Thank you all. I'll see you at the public talk.
Thank you, Praveen. Thank you.